Okay, so here we have the rate expression. Both reactants are included, raised to their orders, n prime. Okay, if they don't tell me what they are, I just leave it like that. If they tell me what they are, then I would include it. If they say A is first order and B is second order, then I would write it rate equals the rate constant times the concentration of A, first order, times the concentration of B, second order, squared, B squared. Okay? So they have to tell you what that order is. So here is an example from an actual equation. Methane plus oxygen produces carbon dioxide and water. Okay? The rate is equal to the rate constant times the concentration of methane times the concentration of oxygen raised to their orders n and n prime. Okay? So this is how I would write it if they didn't tell me the orders. If they tell me the orders, then I would include them. Okay? Now, what some people are going to be tempted to do is they're going to be tempted to see this number 2 right there, and they're going to be tempted to say that this is second order because that's a 2. And the reason you're going to be tempted to do that is because in equilibrium, that's what we would do. And we're going to see that in just the next section. But with rate, you don't. You do not use the coefficient as the order in rate. You do use the coefficient as the order with an equilibrium equation, but not with rate expressions. Okay? So this is not necessarily second order. They have to tell you what the order is. Okay? You cannot use the coefficient. They have to tell you. So, write the form of the rate equation for the oxidation of ethanol. The reaction has been experimentally determined to be first order in ethanol and third order in oxygen. Okay? So, the oxidation of ethanol reacting with oxygen. We don't need the balanced chemical equation. All we need to know is what the reactants are, and we can write this rate expression. Rate is equal to the rate constant times the concentration of ethanol times the concentration of oxygen. Now look what they told you. First order ethanol, third order oxygen. So I'm going to cube O2, and I'm going to leave this one just as it is. Okay? So it's understood that that 1 is the exponent if we don't write it. Okay, so that's how I would write rate expressions. You don't have to calculate anything. You just have to be able to recognize if it's written correctly or incorrectly. You just simply have to choose from multiple choice question which one is correct versus not choosing the ones that are incorrect. Okay? All right, equilibrium. So what is equilibrium? Equilibrium is a process that occurs in both directions, meaning I have a forward reaction and I have a reverse reaction. So if you have a forward reaction, so as I have two reactants, they react and they form product. As that product is formed, it then reacts, the product reacts and then forms more of the product. And it's going back and forth. Okay? Lots and lots and lots of chemical equations are reversible. They are equilibrium equations. They establish equilibriums. Okay? So, what is the definition of equilibrium then? It's the rate of the forward process in a reversible reaction is exactly balanced by the rate of the reverse process. Okay? Sure, yeah, that's very confusing what they just said. The forward reaction is going just as fast as the reverse reaction. That's when equilibrium is established. What equilibrium is not is when you have the same concentration of both product and reactants in the equation. Okay? So, in other words, 5 moles of methane Okay, so let's say this was a reversible reaction, and I had 5 moles of methanol and 5 moles of O2. If this reaches equilibrium, that does not mean that I have 5 moles of these as well. That's incorrect. Okay, these could be 0.3 moles of this and 0.3 moles of this. Okay, and this process could be in equilibrium. Equilibrium just simply means that the rate of this reaction to form this is the same or is just as fast as the rate of this reaction going backwards. So at these concentrations, the rate going backward is the same as the rate going forward at these concentrations. That's what equilibrium is. It's when the rates are the same, not when the concentrations are the same. It doesn't mean I have the same amount of stuff on both sides of the reaction. It simply means the forward reaction and the reverse reaction are the same. Okay? Let's see here. Okay, let me see if we can kind of demonstrate this here. Okay, so let's say I have 10 molecules of a reactant A, and it reacts with 10 molecules of B. Okay, so at first, this is what I have. A and B, they're reacting. Okay, they're in this vessel, they're going to collide, they're going to react, and so let me increase the temperature a little bit so we can get this thing going a little better. Okay, so now do you see what happened? Now I have 9 of A and B, and I have 1 of A, B, and C. Okay? This is at equilibrium. It has now been established. Equilibrium has now been established. The rate of the forward reaction is the same as the rate of the reverse reaction. Okay, it's going to fluctuate a little bit. But you can see it does not mean that these are equal. It just simply means that the processes, the rates of the processes are the same going back and forth. This is an equilibrium equation. Okay? So that's what we mean by equilibrium. Okay. So an example of an equilibrium process would be the dissolution of sugar into water. So you add 2 to 3 grams of sugar into 100 milliliters of water. It all dissolves, all of it. Okay? You have not reached equilibrium. But if you add 100 grams of sugar in 100 milliliters of water, okay, not all of it will dissolve. You can sit there and stir it, and it's not all going to dissolve. It's too much sugar to dissolve into 100 milliliters of water. So, over time, you observe no further change in the amount of the sugar that's dissolving. Okay? So we could make the assumption that no more of it is dissolving. But that's an incorrect assumption. Okay? It appears nothing is happening. However, what's happening is the sugar is dissolving into the water just as fast as it is precipitating out of the water. That's what we say is an equilibrium process. In and out at the same rate. So it appears that nothing is happening. We have established an equilibrium between solid sugar and aqueous sugar. Okay, the forward and reverse reactions are the same. I might have 98 grams of the sugar dissolved and 2 grams of the sugar not dissolved. So it's not that there is equal concentrations of sugar in and out of the solution. It's that the process has reached an equilibrium, okay, of rates. So the double arrow serves as an indicator of a reversible process. Okay. Continuous changes taking place. We can't observe it, but that's what's happening. State of a reaction in which the rates of the forward and reversible reactions are equal will be our chemical equilibrium. Equilibrium reactions that do not are chemical reactions that do not go to completion, meaning it's not ever going to go all just one way. If it does just go all one way, then that's not an equilibrium reaction. But there are a lot of reactions that are reversible. They will go forward and backwards during the reaction. They will establish an equilibrium. Okay? And then no further observable changes are measurable. Okay, so here we have nitrogen plus hydrogen produces ammonia. They're saying this is a reversible equilibrium reaction. Okay? So we have to collide the molecules together like we saw in that simulator earlier. They're going to collide. These bonds will break. And then as the bonds break, then we will reform the bonds to form ammonia. But then ammonia itself can decompose back into nitrogen and hydrogen. And there will be a rate at which that happens. So once I start to build this concentration of the NH3 up, eventually, okay, it's going to push backwards. And once I get enough of it, it's going to push backwards fast enough that it will match the rate of the forward reaction, okay, until that equilibrium is established. So here we can see that happening. NH2 and H2 are reacting. They're reacting. And their rate is such that eventually it reaches this point where the decomposition of the NH3 and the formation of NH3 are the same. And then you've reached your equilibrium point. But the concentrations of these are not the same. They're not the same. Okay, so like I said, when we write equilibrium expression equations, we do it by using the coefficients. So here is an equilibrium expression equation. I want to, this is the general format, okay? Here's the reaction, A, B, C, D, right? A plus B forms C and D. So my products, let me rewrite this, KQ, the equilibrium constant, is determined by knowing the concentrations of the products and dividing them by the concentrations of the reactants. Products over reactants. That's how I always write an equilibrium expression. Products over reactants. So CD on top divided by AB on the bottom. And look, do you see their coefficients here? I raise it to their coefficient. That's their order. The order of the products is raised to their coefficients, and the orders of the reactants are raised to their coefficients on the bottom. So I do use the coefficients when it's equilibrium. I do not use the coefficients when it's rate. That is usually something that's difficult for people to get straight in their head because they just want to do it this way because it's so easy. I just use those coefficients. It's so easy. But then you get a rate question and you try to do it and you get it wrong. Okay? So you need to remember there's a difference when I'm writing these. So here's my reaction. I want to write the rate equation for it. Okay? So you can see here that the rate constant for the forward reaction divided by the rate constant for the reverse reaction would give us the products over the reactants, and that's how we get this for the KEQ, which is the equilibrium constant. Okay, so the forward reaction includes these. So if I'm solving for KF, it would include those on the bottom there. If I'm solving for KR, it includes this on the top, and that's going to equal my equilibrium when the forward and reverse reactions the ratio of them will give me my rate constant, or my equilibrium constant, okay, which equals, don't ever worry about this anymore. You don't have to worry about that ever again. KQ equals products over reactants raised to their coefficients. Okay? So what would be the order of NH3? It would be second order. What would be the order of N2? Just one, it's first order. What about of H2? 3, right? That's how I would write this rate equilibrium expression. Okay? Just like that. Okay. You have to have a balanced chemical equation to write equilibrium constant expressions. So each chemical equation has its own unique KEQ. So all the KEQs will be different for the different reactions, for the forward and reverse reactions of those. The brackets represent molar concentrations, so the brackets are the concentration in molarity. Okay, that's what that would indicate. They are unitless equilibrium expression constants. Okay, equilibrium constants are unitless. Concentration of gases and substances in solutions are shown, meaning that if I have an equilibrium expression with a solid in it, then I don't include that in the equation. Why? Because solids don't have concentrations. A concentration is how much gas is in this area, or how many molecules of something are dissolved into this much water. That's a concentration. If it's a solid thing, it's pure solid, right? There's no concentration to it. So we don't include that in the equation. Okay? If it's a solid or liquid, you don't. So if water is one of your products in the reaction, then you won't include the water in the equilibrium expression. Okay? So concentrations for pure liquids and solids are not shown. So here, these are all gases, so I will include everything in my equilibrium expression. My KEQ is products over the reactants. So HF, concentration of HF, over the concentration of H2 times the concentration of F2. And I'm going to raise those all to their coefficients. HF has a coefficient of 2, and these others are coefficients of 1. That's my KEQ. Okay? So that's what my KEQ is going to be equal to. That's how I write the equilibrium expression. Here's another example. Look at this. Solid. Look at this. Liquid. Here's my KQ. We do not include those, right? MnO2 is not here. H2O is not here on top. MnO2 is not here on the bottom. Why? Because they're solid and liquid forms. So we don't have to include them in the equilibrium expression. Okay, we leave them off. All right, so what does an equilibrium constant tell me? What does it tell me? It tells me which is greater, products or reactants. During the equilibrium, what do I have more of? Do I have more product or do I have more reactant? Okay? So larger values of KEQ indicate the numerator is greater than the denominator. So remember, KEQ is equal to products over reactants, right? So if my numerator, my top number, is bigger, so let's say my KEQ was equal to 20 over 5. So because this is bigger, so 20 divided by 5 is what? 4. Okay? So because this is bigger, this number is greater than 1. So if I have an equilibrium constant that is greater than 1, that should tell me the top number is bigger. the products are bigger, they're greater. So in this equilibrium, this is where the equilibrium lies. It lies toward the product side. That's where I have the greatest amount of stuff. Okay? It's over on the product side. The reactant side is lower. Now, what if it was reversed? 5/20. Okay? Would this number be greater or less than 1? Less than 1, right? So if your KEQ is less than 1, what does that tell you? It tells you that this is greater. What is this? Reactants are greater. That's how you interpret your KEQ. Simply by looking at it as whether it's a greater number than 1 or a greater number than 1. Okay. A number greater than 1 or a number less than 1. And that's going, if it was just 1, that would mean they're equal, right? They're equal concentrations. Okay. All right, so that's how we would interpret those. So here we're going 2NO2 is producing N2O4 in equilibrium and is decomposing back into NO2, back and forth in equilibrium. Okay, and we can see that process once again happening. So once the two rates are equal, we'll be at equilibrium. Okay, but do you see how much this decreased and how much this increased before they established an equilibrium? So I have more N2O4 than I do NO2. This is concentration. NO2 had to decrease this much, had to react and form more N2O4 before that would push back into an equilibrium equation. So this is in the greater amount. So this is a product. So would my KEQ be greater than 1 or less than 1? Greater than 1. My KEQ would be greater than 1 because the product concentration is higher than the reactant concentration. Okay, so here's an example. So HI placed in a container comes to equilibrium. The equilibrium reaction is this. HI is decomposing into H2 and I2. Okay? So here's my equilibrium expression. The concentration of H2 times the concentration of I2 divided by the concentration of HI squared, because this has the coefficient of 2. These are the concentrations at equilibrium. HI, 0.54. H2, 1.72. I2, 1.72. Okay? So 1.72 squared divided by 0.54 squared, 2.96 divided by 0.29 is 10.1. Okay? 10.1. This is a greater number than this. So my product concentrations are greater than my reactant concentrations. And so we get a 10.1 KEQ. Okay. So when they give you the concentrations, you should be able to calculate those. So if they say these are the concentrations at equilibrium, then the first thing I have to do is be able to write the correct rate expression and then simply put those concentrations where they go in the equation. Okay? And I'll be able to calculate my KEQ that way. Okay, let's talk about Le Chatelier's principles. Le Chatelier's principles help us predict changes in equilibrium based on whether I increase or decrease concentrations or temperatures or pressures. Okay? And what we call that is we say that we're stressing the reaction. So it's at equilibrium, it's all happy, and then we do something to it, we mess with it, and it gets all irritated and stressed out. So it has to re-equilibrate so that it can get back to where it was. So if a reaction is at equilibrium and then I change something, it will change everything else until it can get back to equilibrium. So another way to think of this is my equilibrium constant is a number that stays constant. So let's say that my products over my reactants is equal to my KQ. Okay. Let's say my products are 10 and my reactants are 2. So my KQ is 5. Now let's say that we change the amounts of reactants that we have. Let's say we increase the concentration of the reactants. So it's at equilibrium, it's all happy. Its KQ is 5. Okay? So then we change the concentration of the reactants, and everything has to shift. And it shifts in such a way that, so if we increase, let's say we increase this reactant, and it reached equilibrium now, and it's at 4 instead of 2. This number stays the same because that's the equilibrium constant. That's what equilibrium has to get to. It has to reach 5 again. So if I increase this to 4, what's it going to do to here? It becomes 20, right? So it had to, if I increase this to 4, then I'm going to have to cause this to change as well until it equals 5 again. Okay? So that's what I probably actually increased this to like something like 8, and then I had to bring it down to reach 20 and 4 to get to back here to 5. Okay? And now it's at equilibrium again, and it's fine. It's not stressed anymore. Okay? So if you irritate the reaction, it's going to shift until it gets back to equilibrium. Okay? I was going to say something. That's like how my wife is. I get her all irritated, and she has to re-equilibrate until she's like, okay, I'm better. Okay? Okay, so adding NH3 to the system causes it to be stressed. So here, if I increase the concentration of NH3, what is this going to have to do to re-equilibrate? How is it going to shift? So what we're going to do is we're going to say it either shifts to the left or to the right. If it shifts to the right, that's the product side. If it shifts to the left, that's the reactant side. Which way does this, if I increase NH3, everything else is the same, and I increase NH3, how is it going to have to shift to the left or to the right so that it can re-equilibrate? It's going to have to shift to the left. Why? Because it needs to bring this NH3 concentration back down. So it's going to decompose it into these so that these can be brought up. This comes back down until everything reaches equilibrium again. And now it's not as stressed. Okay? It's at equilibrium. Okay? So if you ever increase the concentration of something in a reaction, it will always shift away from it. The shift will be away. Always. So if I had increased N2, which way would it shift? To the right. If I increase H2, which way does it shift? To the right. Okay? Until it can find its equilibrium again. All right? So that's what it's going to do. So if we come back here, we see this has reached an equilibrium. Okay? It's not equal concentrations on both sides, but it's reached an equilibrium. Well, what happens if I increase the concentration of one of these? Okay? Do you see how it has to shift? Okay? It's going, so I increase the concentration of this, AB, and you see what it's doing? It's pushing this way, right? This is going to practically get depleted because it has to push over this way to relieve that stress that I just put into the system. Okay? Because, so now you see, it's like this is almost gone because I had to push it this way to relieve the stress of this amount of that product. And it shifted that way and increased the concentration of those reactants.
So it's kind of like a negative feedback system almost?
Kind of. Okay? Now, if you decrease the concentration of something, now which way is it going to shift? That's right. It's going to go to the right now. Okay? So I decrease the concentration of that, and it's going to push back the other way. Okay? So it's starting to push back. Giving these things some time to react over here. And it's going to start to, so if I decrease these are going to start to build back up. Okay? We'll come back and look at it. Give it a minute. Okay. Okay, so if I decrease the concentration of H2, which way is this going to shift? So if you increase the concentration, it shifts away from it. If you decrease the concentration, what do you think it's going to do? Shift towards. It's going to shift towards it. Because if I decrease H2 here, what does the equilibrium want to do? It wants to build it back up. So it's going to start decomposing NH3 to build the H2 back up, okay, until it can reach equilibrium again. So if you decrease the concentration of something, it shifts towards that thing. If you increase the concentration of something, it shifts away from it. Always. It's always the case. Okay? Removing material decreases concentrations. System will react to the stress to return concentrations to their appropriate ratios. So it's going to try to build it back up. So it's going to shift towards it. So here's an equilibrium equation. Iron thiocyanate in equilibrium with iron and thiocyanate. Okay? So you can see the red iron thiocyanate, the yellow iron, and the colorless thiocyanate wouldn't be seen. Okay? But there's a shift in the equilibrium. So you can go from here to here and back again. You can change those equilibriums simply by increasing concentrations of something or reducing the concentration. So this is the reaction at equilibrium. Shift to reactant with more red color, and then you can shift it to product with the loss of red color. Okay? So here's another example, but this one is dealing with heat. So concentrations, we can change concentrations by increasing them, shifting it away from, or decreasing them and shifting it towards them. Okay? Heat is the same exact way. The only difference is you need to know how to write the heat in the equation. Where do I put the energy in the equation? Well, if it's an exothermic reaction, then the energy needs to be written as a product. If it's an endothermic reaction, I need to write the energy as a reactant. Because it's absorbing energy, endothermic, it's a reactant. It's releasing energy, exothermic. Okay? It is a product of the reaction. If you write the temperature or the energy correctly into the equation, then it acts just the same way as concentration. If I increase the temperature, it shifts away. If you decrease the temperature, it shifts towards. That's how Le Chatelet's principles work. That's how we predict the shift. Okay? Okay? You treat it as increasing the amount of a product. You would shift away. So here in this example down here, we see the shift between blue and red based on temperature changes. So here we're increasing the temperature and it goes blue. Here we're decreasing the temperature on ice and it's going red. okay? And you can just go back and forth, heat, cold, hot, cold, and make that thing shift colors all day if you wanted to, okay? So here's an endothermic reaction. Here I would say 39 kilocalories, okay? So if I increase the temperature here, it's going to shift towards NH3. I'm going to make more NH3. If I decrease the temperature, I'm going to decompose the NH3 into N2 and O2. So temperature or energy works exactly the same way as the concentration of a reactant or a product. If you increase it, it shifts away. If you decrease it, it shifts towards. Okay? Pressure is a little different because pressure doesn't deal with the concentrations of things. So once your system reaches equilibrium, then what you have to look at is the actual chemical equation and decide which side has less moles of gas to determine which way this is going to shift with pressure changes. Okay? So when pressure goes up, shifts to the side with less moles of gas. When pressure goes down, shifts to the side with more moles of gas. So let's see if we have an example of that. So here this is in equilibrium. It's all gases. N2 and H2 produce NH3. Okay? This is a gas reaction. This is a gas reaction. So let's look at the first one. If increased pressure, which way will this equilibrium shift? So what we have to do is we have to count the number of moles of gas. How many moles of gas do I have on this side of the reaction? I have 1 nitrogen and 3 hydrogens. How many moles is that overall? 4 moles of gas. How many moles of gas do I have over here? 2 moles. Yikes. 2 moles of gas. So if I increase the pressure, which side is it going to shift to? If I shift it to the 4, that's going to cause the pressure to continue to increase. If I shift it to the 2, it's going to bring the pressure down. So if I increase the pressure, what does it want to do? Left or right? Right. It wants to go to the 2 moles to bring the pressure back down. Okay, if I increase the pressure and it's all stressed out, what does it have to do? It has to try to bring that pressure down to re-equilibrate. How does it do that? It does it by shifting it to the side with the least number of moles of gas. Okay, that's what it does. How many moles of gas do I have on the reactant side here of this equation? 2 moles. How many moles of gas here? 2 moles. So if I increase the pressure, which way will it shift? It can't shift either way, right? It's not going to do anything. It can't. There's nowhere that it can shift that will change the pressure. So it will just have to stay at that pressure. Okay? So no shift in the equilibrium. This increases pressure, favors decreased volume with more products, 2 moles formed, less products, 4 moles, or less reactants. Okay? Okay. How about a catalyst? A catalyst has no effect on equilibrium. It increases the rate of both the forward and reverse reactions equally. So it doesn't affect an equilibrium. This is kind of a famous question. So, you know, how does a catalyst affect equilibrium? It doesn't. What do catalysts affect? They affect the rate of reactions. They cause reactions to go faster, but they do not determine how much product or reactant you have on either side of the reaction. They just simply allow you to get to that point faster. So they don't change the concentrations. They just allow you to reach those concentrations, those equilibrium concentrations, in shorter amounts of time. Okay, and that's what a catalyst does. Okay, so that's the end of chapter 7. So next time we'll start chapter 8. Make sure you're doing your homework, getting your homework done, so it doesn't sneak up on you. We just have a few more weeks, right? And there's even a Thanksgiving holiday in there. Okay, when you come back from Thanksgiving break, you're going to have a test. Okay? So, and then the next class after that we'll review for the final. And the week after that we'll have our final.